So hello everyone, this is our question. So first see for yourself, then come back to the solution. This is an RC circuit, the pulse waveform, but at the let me choose my pen. Hmm. But at t less than 0, this pulse is minus 1 volt, and then at t greater than 0, it is pulsating wave. Okay, so let's solve the question. Okay, in t less than 0 time frame, in t less than 0 time frame, we assume the circuit in steady state. Okay, actually this is a tricky question. If you do by yourself, then it is good. Otherwise, no problem. I am here for solution. uh, in t less than 0, we steady state में. So at steady state means s is equals to 0. So cap opens, capacitor opens, circuit look like this, resistor and this. It is like a resistor divided circuit with equal resistance, and the input is minus 1 volt. We can see this is minus 1 volt input. So half of the input drops to this resistor, half of the input drop to this resistor, means this is minus zero point 0.5 volt, and this is also minus 0.5 volt. Okay, so what is happening here? uh, at this register, minus zero point 0.5 voltage appears there. uh, so same voltage appears on this capacitor, means this capacitor. mm, this capacitor, I am denoting this as VC. In steady state, uh, this capacitor reach to minus zero point 0.5 voltage, minus zero point 0.5 volts. Okay, this is in steady state condition, and the Vout1 and Vout1 is also minus zero point 0.5 volt. So if we analyze the circuit in t is equals to in t 0 plus time frame, in t0 plus time frame, in t0 plus time frame, we can see we can see pulse input is there, and this and the circuit will look like this. This is resistor, this is resistor, and now this capacitor act as a voltage source with plus minus supply, which is minus 5 volt, and this is the resistor, and this is in. And one more thing, we will verify all this in the simulation. I have done the simulation for this circuit in the LT5, so we can verify the output we are getting in the from the solutions. Okay, so this is my minus 5 volt, and this is V out. So if we write a KVL equation there, this capacitor is VC. So VC is the difference between V input minus V out, V in minus V out. If we rearrange this equation, we get the V out as V in minus VC. Now for this time frame, okay, one more thing is there. In uh, the time period for this pulse is 20 milliseconds, and the on time is 10 milliseconds. Okay, I forgot to mention before. So now we can see. Yeah, now we can see that time period for the circuit is time period for the circuit. Okay. So time period for the circuit is 20 millisecond, and on time period for the circuit is 10. Sorry, on time period is wrong. Sorry. The this time frame is 10 millisecond, and this is also 10 millisecond. Okay. So at t is equals to 0, t is equals to 0 plus, we can see the plus plus 1 volt is there, and VC is at minus zero point 0.5 volt. Okay, minus zero point 0.5 volt, so minus zero point 0.5 volt, and V out is now we can see that at t is equals to 0 plus V out is minus 1.5. So this is our first expression. This is an important expression, like V out is minus 1, sorry, V out is 1.5 volt at t is equal to 0 plus. Now uh, as the cycle moves, like this is the input cycle, and this is 10 millisecond, and this is a 10, and this is 10 millisecond. uh, and also if we calculate the time period of the time constant for the circuit, time constant for the circuit is time constant for the circuit is we will off the input. So these two resistors come in parallel, and this capacitor is also in parallel. So in the R equivalent and C equivalent will become, R equivalent is R by 2 and C equivalent is C. And we can see, if we solve, we will get 50 into 10 raised to the power 3 multiplied by 0.8. The capacitor is 0.8 microfarad into 10 raised to the power minus 6. We can see that this tau constant, tau is 40 millisecond, which is far greater than the time period of the which is greater than the time period of the pulse. So we can say that the time constant for the circuit is greater than the time constant of the circuit is greater than the time period of the pulse. So we can see, sorry for the disturbance. So we can okay. So we can say that time constant of the circuit is greater than time constant of the pulse, means the capacitor will not discharge fully and not charge fully. Okay, so initially at t is equals to 0 plus, cap voltage is minus zero point 0.5 volt. But as time moves from 0 to 10 millisecond, if we move from 0 to 10 millisecond, cap voltage will decrease, as it is plus 1 volt, and it is connected to this plate. So it will charge this capacitor reversely, but it will not to charge the capacitor fully. Means the capacitor will not discharge fully. It will discharge to some extent, like we can calculate as well. How can we calculate the discharging expression for the capacitor is, we say is v v initial or v final, whatever we have, e minus t by tau. Okay, so I am ignoring the sign currently. So I want the capacitor voltage at t is equal to 10 millisecond time frame, 10 milliseconds time frame. So our t value will become 10 millisecond, and our tau is 40 millisecond. We calculate the time constant for the circuit is, so V initial is 0 0.5 volt into T is 10 and tau is 40. Milli to milli is cancel. If we calculate, we get the voltage. Voltage of capacitor is voltage of capacitor at t is equals to 10 millisecond will become 0.3894 voltage. It is in minus sign. So, this is the circuit and this is the capacitor. So t is equals to 10 millisecond, the voltage in capacitor becomes 0.3894. Okay, and at that time v in at that time v in is 1 volt. So we can find out the v out. V out will decrease as the v out will decrease as the VC is decreasing as well. VC is decreasing because V out is the difference between V in minus VC. VC in is negative, so V in is 1 volt minus minus of 0.389. So output voltage at t is equals to 10 millisecond is 1.3894 volt. Okay, this is our V out at that time. So now at t is equals 10 millisecond plus means we are let me draw the input waveform here. Like we analyze for this time frame, this is minus 1 volt, this is 1 volt. Now we are at this, which is t greater than 10 millisecond time frame. In this time frame, the V input is minus 1 volt, and the capacitor voltage, we calculate capacitor voltage is minus 0.3894 volt. Okay, 0.3894 volt, and we can calculate the V out at this time. So V out is the difference between V in minus VC. So VC is minus 1 volt minus VC, and VC is at that time at this time VC voltage is minus 0.3894, and if we solve this, we will get the voltage to minus 0.6105 volt. This is our V out. Actually, this is the calculation part. And now if we plot this waveform, now we plot this waveform. Let me draw here. This is our uh, okay, wait a minute. Uh, okay, so this is our V input, and we have to plot the V output. Uh, Now we can plot V output at t is equal to 0. T is equal to 0. We see that V out is V out is 1.5 volt. So this is 1 volt. So we will mark this as I will write this as 1.5 volt. Okay, because this is 0.5 volt. So I will mark this as a 1.5 volt and 1.5 volt. Okay, now at t is equals to 10 millisecond. This is 10 millisecond. At t is equal to 10 millisecond. V out is 1.3894 volt. 1.3894 volt. And this is 1.5 volt. So 1. What is 1.3984 is somewhere here. Okay, I am marking this as, and now at t is equals to 10 millisecond, the V out will become 0.6105. Okay, it is minus 1 volt, and this is minus 0, not here, around here, 0 point minus 5 volt. So 0.6105 volt is around here. Okay, so it will follow the curve to here. Okay, अब क्या होगा, अब वापस से जो हमारा -1 volt आ गया. अब we see the circuit. if we see the circuit is this. This is capacitor. Okay, this is capacitor and this is minus 1 volt. Minus 1 volt will charge the capacitor reversely. Okay, it is charging the capacitor. Initially, the capacitor has 0.384 volt. Okay, now if the capacitor will charge in this direction, then its voltage increase. Its voltage will increase, but as the time constant, as the time constant is greater than time period of the circuit, as the time period of the pulse, capacitor will not charge to minus. Capacitor will not charge to 0.5 volt. Okay, the charging speed will decrease. The charging speed of this capacitor will decrease in this time frame. So this is minus. This is minus 0.6105 volt. So if let's suppose uh, the capacitor will charge to some uh, 0.4 volt, I guess. If the capacitor voltage increase, the capacitor voltage increase, the V out will decrease magnitudely, but in the negative axis, it will the voltage will rise. Voltage will rise to this value. Okay, voltage will rise to this. Voltage rise as this. Voltage rise as this. Now again we have the positive 1 volt, the positive 1 volt, and the some in initial voltage. We can say that this is as zero point 0.4 volt. This is not the exact value. I assume this is minus 0.4 volt, and this discharging capacity charging of the capacitor is slow in this cycle. And after that the one after that one volt is one at 20 millisecond. 20 millisecond, the 1 volt will appear again in the input. uh, in one Then V out will be in minus of minus VC. Minus, this is 1 volt, and now the voltage is 0.4 volt instead of 0.5. So it will 0.4. The overall voltage will become 1.4 volt. Okay. So the output will, this is 1.4, 1.5 volt. I am assuming this is 1.4 volt. Okay. So the waveform will look like this. This is 1.4 volt. It's not exact. I'm just assuming this is 1.4 volt. Now the cycle repeats. The capacitor will discharge again. The discharging rate for this capacitor is slower as compared to this in this time frame. So slowly decrease. It will slowly decrease, and then cycle repeats again. Cycle repeats again. Now it will reach to this point. Uh, it will reach to this point. Then again it will start. But as we can see, the discharging rate of this capacitor is slower as compared to this, and the charging rate of this capacitor is discharging of this capacitor at this stage is slower as compared to this. Here the capacitor is charging and here the capacitor is discharging. So we can say the charging and discharging, the charging. This is the output waveform, but the charging of capacitor is like this and discharging of capacitor like this. The charging, discharging of capacitor are one is decreasing per cycle. So at one time, at at every the charging and discharging of the capacitor are decreasing every period or every time frame. Yeah. So we can see at one time the charging and discharging of capacitor will equal, and at, at this time frame the volt the output voltage at this time frame the output voltage, this is our input and this is our input, the output voltage will ripple on the input. It will like this. like everything is same, but the output voltage will look like this as a ripple. Cause why this ripple is a charging and discharging cycle is same, so we will see the ripples here at 1 volt. This is the steady state. This is the steady state for this circuit. Okay, this is the steady state for this circuit. Like we see ripples here. Okay, and for this type of circuit, for this type of circuit, we can also calculate the ripples. We can calculate the ripples. The ripples for this circuit is the ripple for this circuit. Ripple for this circuit is Vx t by 4 tau. And what is the Vx? Vx Vx is the Vx is the this voltage. This is 2 Vx. Okay. So in our case, what is Vx? This is 1 volt. If we equate 1 volt to Vx, so our Vx will become, let me check one thing. So sorry, not Vx, it is Vx by 2. So uh, let me draw here. It will become chaotic. This is Vx by 2 and this is minus Vx by 2. At steady state, ripple will appear on the output, but the steady voltage is 1 volt. This is the steady state output for this circuit. Okay, so this is Vx by 2. This is Vx by 2. In our case the ripple voltage is 1 to minus 1 volt. So 1 volt will equate to Vx by 2. So we can say that Vx is 2 volt. Okay, 2 volt. If we put in this, we can calculate the ripple. We can calculate the ripple. And what is the ripple value? Ripple value is uh, 2 volt and time period is 20 millisecond. 4 into 40 millisecond. Millisecond to millisecond is cancelled. Uh, this is also cancelled. We get 1 by 4, which is 0.25 volt. Okay, this is the ripple voltage. So we also calculate the ripple voltage. This is the ripple voltage. Like I will draw separately. I am drawing this in the steady state of the circuit. Like what is the steady state voltage look like this in the output. Okay, this is 1 volt minus 1 volt, and in the steady state we will see the ripple, but over on the input voltage. Okay, the it will follow like this, the same waveform, but with the ripple. Of course, I will explain this later. Why is this happening? So okay, and the ripple voltage is delta V is 0.25 volt. We can see all this value in the simulation as well. So why we see this voltage and voltage as a ripple? Uh, if we go back to the circuit, this circuit is a high pass filter. High pass filter, how high? If we calculate the transfer function of the circuit, transfer function for this circuit is R upon R plus the parallel combination of R and C. If we expand if we expand this transfer function, we will get to know that this circuit is the high pass circuit, high pass filter. What high pass filter do? High pass filter will pass the high frequency and attenuate the low frequency. But and the input we have is the uh, high frequency input. So it will pass the high frequency, and then it will pass the high frequency, and at steady state it will achieve it will pass the high frequency, but at steady state it will achieve the input, means it will catch the input. like क्या हो रहा है कि हाई फ्रीक्वेंसी पे ये हाई हाई पास फिल्टर है, तो ये क्या करेगा, फ्रीक्वेंसी को पास कर देगा फ्रीक्वेंसी को, बट एट द स्टेडी स्टेट पे क्या करेगा कि वी इनपुट को कैच करने की कोशिश करेगा, बट ये एग्जैक्टली कैच नहीं कर पाता ड्यू टू लॉसेस एंड ड्यू टू रिपल. That's why due to losses, that's why we see the ripple on the circuit. This is the initial stage of circuit where the transients are occurring, but at the time passes, the circuit will reach the steady state, and the output waveform, this yellow one is the output waveform of circuit. This is the steady state of the circuit. Okay, with the ripple 10 0.25. And how we calculate the ripple formula is vxt by 4 tau. We will derive this later, but as for now, for now learn this. Whenever there is the pulsating voltage is this voltage variation vx by 2 minus vx by 2, then the output ripple for the circuit is delta v, which is vxt by 4 tau. Tau is the time constant of the circuit. T is the time period of the pulse. Okay, if we put these all these value, we will get the 0.25 volt. Now for the simulation results part, uh, we will verify the we will verify our results to the simulation. Okay, so for the results, like first uh, so this is the circuit, and this is the simulation part. First, this is schematic, sorry, circuit diagram. With the pulse, I define pulse. Pulse is there. Like this, -1 is the initial, t is less than 0 voltage. This is 1 volt, and this is the zero delay, rising and fall time, which is in nanosecond. The t on time period, and this is total time period of the circuit. This is on time period, and this is time period of the circuit. Now, if we see the results, you can see, uh, like I will zoom it. Okay, so at t is equals to, let me take the color pen. At t is equal to 0 second. Okay, so at t is equals to 0 second, we can see this is the 1.5 volt. So simulation is verifying our results. So sorry, this is 1.5 volt, and as time is decreasing, sorry, as time is increasing, the output voltage is decreasing, and the output voltage reached to some value. It is less than sorry, this is the, and this is around 1.3849. As in the result, we verified the result. How much voltage we are getting is 1.894 volt. Okay, so it's roughly at this value. Maybe some of the digits will be changed, but it is roughly 1.3. Okay, so at t is equals to 10 millisecond, we are getting 1.384 nanovolt. Okay, but as we will move to 10 greater than 10 millisecond voltage, we can see this voltage this voltage is minus 0.61, and we also verify, we also get minus 0.61. It is almost, or maybe greater than minus 0.61, means in the magnitude part it is maybe, I'm not getting the exact value what is it, but I am assuming that this is 0.6 volts. So this point is minus 0.61, or maybe greater, like 0.62. Yes, there is some variation, but the exact results are matching our results are matching the simulation. So this is 0.62 volt, and as we increase, like I said to you earlier, that in this stage the capacitor discharged, but in this stage capacitor charging, cap is charging. Okay, as cap charging, the V out is decreasing, so it will reach to this stage. It will not it will not discharge that much, but it will discharge to some extent, and the output voltage will rise, and this is the rising behavior we can see. Now in the next part, this voltage is not 1.5 volt anymore. It is less than 1.5 more, and we can see this in waveform also. Like it is not 1.5 volt anymore. And why this is not 1.5 volt? We verified this in the this in our result, or we solved this in our result. So I hope you are getting my point. Now it will decrease again. It will decrease again, and not reaches to 1 volt, or means the capacitor will not discharge fully. In this, the discharging rate of the capacitor is more as compared to this, because the drop in voltage for the capacitor from here to here is more as compared to here to here. Are you getting my point? Like I will explain again. Like the discharging rate of the capacitor in this time frame is more as compared to in this time in as compared to this time frame. Okay, means the like uh, this is the drop voltage of capacitor, and if we see in this, so this is less and this is more. So, and the in the charging phase we can see capacitor is charging, so and this is more, the charging rate in this frame is more as compared to this frame. Okay, so the charging rate is also decrease. No, wait a minute. Yeah, yes, okay. So charging rate is decreasing, and discharging rate is also decreasing, and at some point we can see we can also see in this waveform, like the charge discharging of capacitor is discharging rate of the capacitor decreasing as this curve is become more flatter and flatter. So now at this point the circuit are going in steady state, and it will achieve a constant ripple, we can see. And why is this happening at these stages? The charging the charging discharging rate and the charging of the capacitor becoming equal, because the discharging rate here is more and lesser and lesser, and we can say, we can say that discharging at this point or this point, the discharging and charging rate of the circuit equals, and hence we will get the ripple in the voltage. And we also calculate the ripple. If we see, like this is 1 volt, and the ripple voltage is like this, and here is also uh, it is less than 0.9 volt, and we are seeing in the waveform that the ripple voltage is 0.25 volt. Like they not exactly 0.25 volt, it may be more or maybe less, but around the ripple voltage is 0.25 volt, which can be verified from the waveform also, because this is 1 volt, this is more than 1 volt, and this is less than 1 volt, not 0.9 volt, but um, lesser than 1 volt. Okay, maybe 0.95 volt, or this is 1.05 volt. uh, Zero if we add this, we will get 0.25 volt. Okay, maybe this is more, this point is 0.1 0.12.5, or maybe this point is also minus 0.12.5, less than 1 volt. Okay, if we add this difference, we will get 0.25. So this is our results, and we verified our simulation, our solution to the simulation results. Okay, I hope you like my solution. If you have any doubt, you can ask in the comment section. Thank you. Okay.